Very good. So we started the course with chapter 1, and in chapter 1 we recap logarithms, exponential functions, and trigonometric functions. So that's all a bit of a background knowledge. So to begin with, we're just going to simplify some logarithms. We're looking at logarithmic laws. And so the first one we have log of 10 root 10. And we are asked to simplify this. So whenever we have log written by itself, we assume it's log in base 10. So that means we want to express this as a single power of 10. And so I'll do it in an elongated manner. We're going to write them first as 10 times 10 to the half, and then we can collect the powers. They have the same base, so we can add the powers. That'll be 10 to the power of 1 plus a half. And now that we've expressed it as a single power of 10, it simplifies to that power of 3 on 2. So log of 10 root 10 is equal to 3 on 2.
Does it specify base 10? Or is it why it's assumed it's base 10?
Yeah, whenever it just says log by itself, we assume base 10. Anytime there's a different base, we should have a subscript there. Very good question. Okay, on to B, we have ln of 1 on E. Now we've got two ways we could simplify this, all right? And I'm going to do both. So the first method that we'll do is we will express it as a single power of E. We can make that ln e to the minus 1. And then ln of e to the x simplifies to x, so this simplifies to minus 1. However, whenever we see logarithms, every time you see them, always pops up in the exam. Anytime you see ln, always think separate. We could write this as ln1, take ln e. All right, we know ln of 1 is 0, and this is ln of e to the 1 simplifies to 1, so we have negative 1. All right, so both of those are ways of arriving at the same answer. Okay, we have for C, we have 3 ln2, take away ln4. So we're going to collect these together to be a single logarithm. But before we do that, we're going to take this power up to the top here. We would have ln of 2 to the 3. 2 to the 3 is ln of 8. And then we have ln A, take ln B, we can write it as ln A on B. Simplifies to ln of 2. All right, and then for D, we have an exponential equation. All right, now we can solve this by equating the bases, or we can solve it by using logarithms. Let's do both processes. So if I want to solve for an exponent, I want to solve for this power using logarithms, what I would do is perform the natural logarithm of both sides. So I'd have ln of 3 to the x take 2 equals ln of 9. Remember, when you perform a logarithm, you're performing it of the entire side. So it's the entire left side and the entire right side. Okay, so x take 2, we're going to bring that out the front as a power. So we have x take 2 times ln 3 equals ln 9. We'll divide both sides by ln 3. So we'd have x take 2 equals ln 9 on top of ln 3. Now that is different from this one here, ln of 9 on 3, okay, they are not the same. And then we'll plus 2 to both sides. ln of 9 on ln of 3 plus 2. All right, now we can take this a little bit further as well in order to get the same answer that we'll get from solving it using, by equating the bases in a moment. First, let's follow this other process through and then we'll correct this answer. So, we can write this, if we're going to solve by equating the bases, what we want to do is express 9 as a power of 2. Because the bases are the same, therefore the powers have to be the same, and we'll plus 2 to both sides. Now this procedure is certainly simpler, more elegant, but we can only do it provided they can be written with the same base. Okay. So how can we make this answer look the same as this one? What we're going to do is we're going to take ln 9 and we're going to recognise ln 9 can be written as ln of 3 squared. All right, and ln of 3 squared, we can bring the 2 out the front. All right, and then ln 3 is common to the top and the bottom, so it can cancel. We have 2 plus 2 is 4. So the reason I'm drawing out all of these parallels is to really demonstrate the rules of logarithmic functions. Okay, so that's exercise 1b. Now, I think just as by way of recap of 1a and 1c, when we're talking about exponential functions, so we have the function e to the x, looks like this, and we have the function ln of x, looks like this, that they are the inverse of one another, okay? So that means they're mirrored about the line y equals x, okay? They're mirror reflections of one another, that's how they're related. And we have e to the x is asymptotic to the x-axis. Therefore, if we mirror it about the line y equals x, then ln of x is asymptotic to the y-axis. And so that's expressed by e to the x will always be positive, and ln of x will never, does not exist for values of x less than 0 or equal to 0. ln of x exists for x greater than 0. So that's what I've meant by both of those comments there. Okay, on to some trigonometric functions. Just to recap these. Now you'll have your calculator for the entire exam, so that's good. But just by way of recap, if we have sine of 2x equals half, and what are we asked to do here? Nothing. Solve for x, I suppose. So if we're going to solve this trigonometric equation, what we would first do is we would consider the domain. Generally, we're solving it over 2 pi, so we're solving it over one interval. However, the 2 here, if we think about what that does to the wavelength, let's sketch the basic sine of x function. That's it there to 2 pi. That's y equals sine x. Now, what's different about sine of 2x, and you can check on your calculator, you might remember, but it means that we have 2 wavelengths in 2 pi. All right, so it squashes it together, and so now we have 2 whole wavelengths in 2 pi. So that's the difference from sine x to sine 2x. Now what that means, we are asked to solve the equation sine of 2x equals half from 0 to 2 pi. So if here's the function, here's half, and these are going to be our 4 solutions, right? So there it's our 4 graphical solutions. When the y value is half, what's the corresponding x value? That's what we're asked to do here. So that's what's going on graphically. Now, because of the 2 here, what we have to do is multiply the domain by 2. Do you remember this? We'll go from 0 to 2x to 4 pi. And what we're going to do is we're going to look at the unit circle. Here's our unit circle. And we're going, when is the y value? Because sine is the y value. When is the y value equal to half? It's going to be at this location and this location. And so on the first revolution, it is pi on 6 and 5 pi on 6. All right, those are the values of 2x, the values of our angle. Pi on 6 and 5 pi on 6. That is within the first revolution. That's between 0 and 2 pi. However, because of the 2 here, we have to go another rotation. So we're going past both of those angles again, and because we go past them, it means we add 2 pi. Is everyone remembering this, or is it a bit of a stretch?
Stretch.
Stretch from year 11 methods, yeah. So we'll have 2x is pi on 6, 5 pi on 6. Now here we can process that in your calculator if you want to, but what we would do is we'd make them have the same denominator. It'd be 13 pi on 6, and plus 12 pi on 6, 17 pi on 6. All right, so we have 2x is equal to those values. So then in order to solve for x, we would divide both sides by 2, which gives us x is pi on 12, 5 pi on 12, 13 pi on 12, and 17 pi on 12. Okay, so that's quite a tricky trigonometric one for us to solve. Why? Because we're considering multiple domains. That's what tends to make it a little bit trickier. All right, certainly these have popped up in our course. I reckon We've talked about solutions to trig equations, and we've even talked about plus k2 pi, where we're considering multiple revolutions. All right, so this might be an area to recap. Certainly I can provide some resources for you if you're interested in recapping that in a bit more detail. So that's sine 2x, okay. The good news is part B will be a lot easier than that. All right, so for part B, we're asked to evaluate tan of 5 pi on 6. Okay, so one way we could do this is type it into our calculator. We would need to make sure our calculator is set in radians. Now, historically, all of the exams have been in radians. Okay, so we've got good inductive evidence to suppose that future exams will maintain that, but we never assume. Okay, so just be aware, keep it in radians unless stipulated by the question that you should put it in degrees. So for tan of 5 pi 6, what I'm trying to draw out here is that tan of theta is equal to sine theta on cos theta. All right, so what we have here is sine of 5 pi on 6 on top of cos of 5 pi on 6. And then we would look at our unit circle. 5 pi on 6 is over here. All right, we established before that the sine value is half. The cosine value is negative root 3 on 2. And then we're just simplifying this. AD on BC, we'll have 2 on minus 2 root 3. The 2's can cancel, so we're left with negative 1 on root 3.
Do you recommend putting the unit circle?
Yeah, if you're not comfortable with it, absolutely. Yeah, I can tick.
Calculator though?
You can just use your calculator. So if you're comfortable using your calculator to generate it, absolutely. Yeah, because you will have your calculator. You'll probably find as well though that you have heaps of space. 2 double-sided sheets, it's a lot of space.
Not really.
It is a lot of space. You'll struggle to fill it. You will. All right. So that's the challenge for you. Fill up both of them. All right. Last one here. We've got a graph, and we're told it's a sine function. We're not told it's a sine function. It is a sine function. Now we're going from 0 to 2 pi, and we're asked to find the equation. So what we can see is that this line here is the principal axis, okay? That's the value of d. So remember the basic sine function is a sine b of x takes c plus d. We've just been doing this with our folio task. It's the way we manipulate functions, right? Where d is the vertical translation. For a trig function, it's the principal axis. It's the line about which the trigonometric function propagates itself. So from our graph, we can see that that occurs at 1. So we have the value of d is 1. We also have the amplitude is the distance from the principal axis to a peak or from the principal axis to a trough. So we're going from 1 to 4, that's 3 units, and from 1 to minus 2, that's 3 units as well. So our amplitude is 3. And then the value of b is how many wavelengths are there in 2 pi? Well, we have 1, 2. We have 2 wavelengths in 2 pi, so the value of b is 2. No horizontal translation occurring there.
Is C the horizontal translation?
C is horizontal translation. Yep, moves it left and right.
Isn't C difficult to see?
Very difficult to see. That's why I tend to ignore it. Very good. Okay, turn the page over there, and we've got here the cheat sheet that we use for rules of calculus. There's a unit circle there as well. I should have pointed to it when we were talking about it. Log laws. It's just a really good summary sheet, this one. So let's flip the page over, and we have 2A, first principles. All right. So
11 tends to the I hate this.
the formula for first principles is f dash of x is the limit as h approaches 0 of f of x plus h, take f of x on top of h. So in our circumstance, our function is x squared plus 2x. So we will have f dash of x is the limit as h approaches 0 of x plus h squared plus 2 times x plus h. All right, that's our f of x plus h. Take away f of x in brackets because the negative distributes, all on top of h. Yeah. See if we can get a darker mark. So, next step, the first principles, fully expand and collect like terms. Okay, fully expanded. Don't forget your limits in every step. Factor and cancel H. Apply the limit. And we knew it was going to be that because of simple differentiation. And when we get to here, once we've cancelled everything, remember this is a checkpoint because everything at the top should have a H in it. If not, backtrack, you've done something wrong, go fix it. Everything up here has a H, so we good. We good. All right. So that's first principles. Next we looked at simple differentiation. And so just to recap the rules of simple differentiation, we have x to the n, and x to the n take 1. We have kx goes to k, and the derivative of the constant is 0. So those are the rules for simple differentiation. Now we're given a complex one here, where we have y equals 3x plus 2x squared on top of x squared. Now before we can differentiate this simply, we first need to express everything at the top of the fraction as a single power of x. So we're going to simplify it first. We'll split the denominator. Alright, so here this one's going to simplify to 3x to the minus 1, and this one's going to simplify to 2. Okay, the function can be expressed like this as long as we keep the same constraints, right? The constraint of this is that it doesn't exist if x equals 0. This function will not exist when x equals 0 anyway, because we have 3 divided by x. Excellent. So notice how we've got y equals equals equals. Now we differentiate. Make sure you use your correct notation. We go to dy on dx of minus 3x to the minus 2, and 2 disappears. And of course, we remember the textbook likes to simplify, although in the exam, frequently says no need to simplify. So read the question carefully. Okay, then we're on to the chain rule. So we have y equals alright. So if we have a function to the power of n, then the derivative is n f of x n take 1 multiplied by the derivative of that function. So here we have x squared take 3x to the power of 5. We have a function to the power of n. So then the derivative is going to be n f of x to the n take 1, and then multiplied by f dash of x. Alright, now I'm going a bit quick, or everyone's keeping up? I'm going too fast, let me know. So then the product rule and the quotient rule are just stated. We've got them there. So product rule when we have one thing multiplying another, u times v, and quotient rule when we have one function divided by another, u divided by v. And then we have two derivatives of exponentials. So we have y equals 2e to the 3x plus 4. This is e to the f of x. And when we differentiate it, it becomes f dash of x, e to the f of x. Alright, so 2e to the 3x plus 4, we can differentiate straight away. This 2 is just going to hang out. And the derivative of 3x plus 4 is 3. And then e to the 3x plus 4. Alright, so the 2 staying there. We have e to the f of x, so f dash of x is 3. And then e to the function. Alright, so that's 2f. Then we're on to 2g. We have logarithmic functions. And we're told y equals ln of 2x to the 3 take 4. So we're confronted with an ln function. The question is, can we simplify it? No, it's not multiplying or dividing. Okay, so we don't have ln of a on b or ln of a times b. So we can't split it. Instead, we're just going to jump straight to the differentiation. Now, when we have ln of f of x, the derivative becomes f dash of x on top of f of x. So here, the derivative will be 6x squared on top of 2x to the 3 take 4. F dash of x on top of f of x. Very good. And our last one then, we have y equals positive 2x. And so the derivative is, so when we have cos of f of x, it goes to negative f dash of x sine of f of x. I'll write this down. Cos of f of x goes to negative f dash of x sine of f of x. So we're going to have, we've got cos of f of x, so we know there's a negative at the front. We differentiate the angle here, so that'll give us 2. And then we have sine of f of x. Negative 2 sine of 2x. Very good. So that's a very brief summary of chapter 2 and chapter 1. So really all I've done there is summarise the